Good morning, everyone,
Okay.
for today's distinguished webinar in series in AI and cybersecurity. Today's speaker is Dr. Utku Kose, full professor at Suleyman Demirel University, Turkey. And Dr. Utku has been also a research associate at UND before. And Dr. Utku received his B.Sc from Gazi University in 2008 as a faculty valedictorian, his M.Sc from Afyon Kocatepe University in 2010, and his Ph.D. in computer engineering from Selcuk University in 2017. Throughout his career, he has held several positions, including lecturer, assistant professor, associate, and at several Turkish universities. He was also a visiting researcher at UND and holds the title of a honorary professor of artificial intelligence at ITM, Baroda University, India. He has authored more than 350 publications, including journal articles, books, and conference proceedings. He serves on several editorial boards of multiple scientific journals and editor of Biomedical and Robotics Healthcare, CRC Press, and Computational Modeling for Biomedical Applications for Existential Risks, Elsevier book series. He's a senior member of IEEE and a professional member of ACM. His research interest includes AI safety, ethics, biomedical applications, optimization, chaos theory, and computer education. Dr. Kose, thank you so much for taking the time for being here with us this morning. And you've been an awesome for our center's efforts in the CARS conference, and I appreciate for your continued support, and the floor is yours.
Yeah. Thank you so much, Dr. Ranganathan. It's great to be here that we'll all together with the C2SR team and also all the people from US, and also I see some people from my place, also some students. So last time when I provide this speech at the distinguished webinar series in AI and cybersecurity, I was in USA in Grand Forks. So now I'm in Turkey. Let's hope that to do the next one in face-to-face again. I'm in a hybrid mode, but I'm in the US, of course. So thank you very much also for the introduction. So I just wanted to, after the kind invitation by Dr. Prakash Ranganathan, I talked about something interesting to talk this time rather than of course, by connecting to something I'm already interested and working on, but rather than talking about something I published or I've already worked on, I wanted to talk about something experimental and also related to the things like XAI, digital twin, and also, of course, for the cybersecurity with some flavor of the AI safety. So for doing this, I've just developed an application as a result of the AI-human collaboration at this point to establish a cyber duel, which is for going through some scenarios of the smart infrastructures and to test how the different attacks techniques and the defensive techniques are dueling in the same environment, and how the different the techniques in terms of attacks and the defensive side are resulting to different outcomes, and how we can just weave them through some XAI and digital twin based interfaces. So let me to share my screen. First of all, I just send the request. I think the presentation is done by another user.
Harish, can you see?
Probably by Harish.
Give me 1 second.
I think now I'm able to. Yeah. It's okay. I'm able to share now. Okay. Yes. So my talk is titled as the Cyber Duel in Smart Infrastructures, Security Analysis with XAI, Explainable AI, and Digital Twin Perspective. I've just wanted to, as I've said before, something experimental to go through some attacks and defensive scenarios, and to go through some already known scenarios from the literature. And at the last time, I also added a few more scenarios to show something related to also some biomedical based applications. So I think it will be giving some ideas about how the AI safety in terms of especially the smart infrastructures is currently just structured or shaped by different attacks and the defensive strategies, and how we can inspire from XAI and also digital twin based outcomes at this point in terms of a common platform maybe. So we know that especially for the cyber physical systems currently, we know that the transformation results to the different issues at the end. So the digitalization of especially energy grids or, for example, critical medical devices maximizes the efficiency, but exposes the physical process to digital infiltration. So that is an issue for the especially cybersecurity. And when we think about the more detailed things such as AI aspects, AI mechanisms, and data-driven things inside such systems, that becomes a top problem in the future of the cybersecurity. So in terms of physical reality, we know that there are power outages, some infrastructure damage, or incorrect, for example, drug dosage when we think about some electromechanical biomedical device, for example, for insulin pump, for example. But when we think about the digital side, there is the digital vulnerability potential. We use sensors, we use some protocols, even wireless, and also we need to manage the AI on the background. So that's just results to some threat vector or the literature when we think about that the attacking side just results to some the design of some threat vectors at the end. So we need to know about that the cyber attacks no longer just steal your data or tries to some damage in your hardware, but they rather manipulate the physical laws and psychological outcomes, for example. So we need to deal with something additional from the data-driven or again AI-based some algorithms or some techniques to deal with such issues. And we need to test the things. We need to go through scenarios. We need to test them. We need to see what can be useful for us. So in my speech, that the XAI and the digital twin perspective will be in the front. But of course, I will be showing you some more different aspects in terms of metrics, the other findings. So I think it will be a good playground for, especially when we think about something experimental. So yeah. So when we think about the machine learning side, when we think about the current developments in terms of the AI hacking the models. There is the problem of that you need to design some perturbation-based data to hack or to manipulate a target machine learning-based system or the model. So there is the decision boundary, for example, when we think about the classification perspective. So there are some microscopic or very small perturbation which is happening at the data level. So that causes the data attack algorithms to manipulate the target model at the end. And of course, the ML-based IDS intrusion detection systems are at this point some susceptible to adversarial perturbations. So these are, of course, the attacks that they have some mathematical background. So they mathematically deceive the model while they appear to us, to human, as the normal things. So the manipulation here that's generally is structured or shaped by throughout or around the decision boundary with the data manipulations. And the blind spot here is that we know that the standard machine learning models cannot detect the threats that deliberately mimic the statistical distribution of normal operations. So that's a problem. And of course, the silent failures in the CPS or the smart infrastructures, the critical systems, just all that need to be carefully analyzed and monitored or tracked accordingly. So that is the general problem, and maybe the feature of the CPS and the developments in terms of the AI attacking and defending techniques need some more additional efforts which are appropriate for the human side or the human perspective. So, of course, even this is a requirement. It's become a requirement. For example, when we think about the NIS2 directive by the European Union in 2023, they need or they just requires the use of the explainable, the XAI decision process in critical infrastructures. On the other hand, the FDA, here FDA MID guidance just requires the cybersecurity risk management and also transparent traceability in medical devices. Or in the US side, the NERC CIP enforces strict cybersecurity standards in especially energy grids, and they also required just some regulations, the mandatory regulations in terms of the CPS connection systems, which should be shaped around some analysis perspectives. So the regulatory bodies just already wants us to develop some user-based, user-compatible tracking to aspects. So the XAI here and also the digital twin, when we think about the digital twin mechanisms that having some real-time tracking and real-time management and even descriptive and predictive capabilities, enhancing the user control over multiple, maybe distributed smart devices, shaping the smart infrastructure ecosystem can be a good candidate, and it can be a good combination with the XAI, explainable AI. And so my speech just went around, my idea went around these aspects, and the result to this the experimental things I will show you, and the outcomes I already will be talking about. So, of course, when we think about the existing literature, we know that, of course, this is somehow the experimental and some different and interesting application perspective you will see. But when we compare the thing I just did with the existing literature, we can say that the research papers or the outcomes are generally just examining some specific attack methods or some maybe single domain. For example, I started with checking some energy grid-based scenarios and ended up to some different things, even including the medical scenarios. Even one of them is also an something imaginary thing, but a realistic scenario, of course, at the end. But we need this is because we need more different domains considered in terms of the evaluation framework for the attacks and the defensive the measures at the end. So in my study, I've considered the smart grid structures and the IOMT scenarios here in one framework. And there are the 7 methods with 30 repetitions in terms of the attacking site. I evaluated them with some metrics. And there are some also for the smart grid aspects. There are some also correlated PMU and the other things, that the THD, the voltage, and also the frequency and the other things are already just included in the data scientist sites in my study. And also I integrated Shapley, a simple Shapley, and also some digital twin-based interfaces, some components which are simulating each of the distributed components, devices, or the things shaping the different smart grid or IOMT or the pacemaker, for example, device-oriented ecosystem. So I ended up to have that's such a common testing and experimental application environment to end up how the things are ongoing, which attack methods or techniques are better, and how about the defensive techniques, and how we can evaluate them from the view of the XAI and also digital twin-based mapping. So I include 7 attack vectors here. You know that the FGSM may be the simplest AI attack method. It's just all uses the machine learning model's loss function, and it calculates the gradient value of this function, and it gets the sign of this the gradient calculated gradient, and also by considering this sign, this direction, just the algorithm just adds some perturbation, a very small number, small noise, accordingly to provide some adversarial sample, which will be manipulating the target machine learning model. So that's not the ending, of course. After this, the research just all went through some iterative methods like PGD, for example. PGD is actually somehow an enhancement of the FGSM, which includes some iterations. So thanks to iterations, you enhance your perturbation better to manipulate the stronger machine learning models when you compare with the FGSM capabilities to manipulate and to make their decisions false, for example. So it's not the ending. Carlini-Wagner CNW is another technique here that it's just considers the problem of the adversarial attacks as an optimization problem. So it's a very interesting thing that it tries to. There is the L2, the norm, which is the distance or the measure we use for understanding how your attacking method just all changed the original data, how it's changed its value or its situation, so that we can understand how much we manipulate the data and so change the data, and so how much we can manipulate the target machine learning model. So as you know, as you can understand, the minimum, the lowest value of the L2 norm here is the most useful one. So the Carlini-Wagner is taking this problem is as an optimization problem. So while manipulating the data samples, it also calculates that L2 norm to minimize it in terms of a minimization problem. So it's also another story of the AI attacks scenarios. And also there's the Jacobian value here. Jacobian matrix are also used for the AI attack scenarios. So JSAM, MA, sorry, the Jacobian saliency map attack is just all using this matrix. After calculating this, it considers that which input, which feature affects the outcome most or more according to others. So it targets some top features, like just take two features, for example, and with the minimum change, it just targets the total whole, the bigger manipulation at the decision side of or output side of the target machine learning model. So there's also auto attack. It combines some of the attack models accordingly, like considering the PGD or the other attacks. So it tries to manipulate the L2 norm, minimize it, and at the end tries to end up to a better manipulation for the target machine learning model. And there's also generative adversarial network-based technique on the other side. It's called as the statistical ghost here. So it uses some generative data, which is produced by the generative adversarial network. As you know, it has some such capabilities. So it produces some fake data and to manipulate the target system. For example, it stays perfectly within normal data distributions, as you can see. I noted it here, and it makes the threshold-based detectors blind, totally blind. So it's also another nice attacking model used widely, especially for black box models. But if you have some black box models as targets, it can be more successful according to other attack techniques. And also there's the FDI stealthy. So this will be a very nice the attack method, because it's just considers the physics constraints. So it's already mimics or inspires from, for example, AC power flow constraints when you consider the grid systems. And also it has the lowest altitude norm values, but it keeps it as a stealthy technique, but with good attack success rates. So it's also a nice attack technique. In order not to deal with the many technical details, I am passing this, but all of these seven techniques were or included in my application site. So when it comes to the defensive side, I used the both machine learning defense techniques and also some countermeasures, which means that some not machine learning oriented, but data driven, data manipulation oriented techniques for ensuring some defensive aspects against the other attacking scenarios. So I run the platform, or I run my simulations by using all the combinations, that the seven to this the different defensive techniques. And at this point, at the machine learning side, I use the Bayesian LSTM, and it's also used for the JAM, which is all using the entropy value, the mutual information thing here for detecting the uncertainty of an attacker's data. Even it's statistically normal, tends to be looking normal. So it just considers that the prediction rate of the model, defended model, seems to be low, then this that just technique just alerts the system and ensures that the attacks just all eliminated. And I also use some example machine learning techniques with the Shapley values for explainability. And also I use the GRU adversarial training sites just with the model. Here is an interesting technique, as you probably already know, that you train your model with some historical attack data, so you make your model robust against the attacks here. So when it comes to other traditional countermeasures here, I use the MTD, moving target defense. It just rotates the target feature space, so invalidate the pre-calculated gradients. So if you are to use the attacker to use the gradient-based attack techniques, it just all fails, because the system just all the defensive technique, this MTD, results to or requires a new calculation of the gradients. So it's also effective against the AI attack techniques which are using the gradient scope, or for example FGSM, as you know, I already indicated at the first. So it's failing in this scenario. And there is also feature squeezing and also randomization. These are two other the defensive techniques. It's all pre-processing heuristics that allows the changing the structural precision of the adversarial attacks. You skews the feature data and also you randomize some data aspects here in your model's data side, so results to the attacking side to be not to be being successful because the model, the data oriented learning aspects of your model is somehow just using the more different that's the input space. So when you squeeze or randomize that input space here, it results to a failure for the attacking scenarios. Okay, so I had 8 different scenarios. I'm not expert of all of these scenarios. Actually, I just went through the literature. I got some real values, and I did my best to simulate the scenarios here. Like there are some events happened around the world, in US, in Germany, and I also designed a few days ago. I also added 2 more scenarios: the hospital IAMT device for the insulin dosing here, and also a pacemaker ICD is also another interesting scenario. So I made the whole thing just not related to only energy grids or energy-based systems, but also including some biomedical aspects, which can be also interesting to you. So I will be explaining them in detail. They are all connected to literature. Some already happened events. Most of them are related to them. And at this point, there is the Mahalanobis measure. It's somehow a different distance measurement. The metric, as you know, like Euclid, like Minkowski, and the Mahalanobis just all use some standard deviation and also use these aspects to calculate the distance better. So, in especially the anomaly detection mechanisms, this measurement, this distance measurement metric is also effective. So, in terms of the different scenarios, whether they are biomedical or grid-based things, I considered, for example, for the grid side, the voltage, frequency, or active power things, and the Koaliski correlation mapping resulted to Mahalanobis detection analysis. So in this way, we just in the platform we can see that the change in terms of the attacking side or the adversarial attack situation widely. So in the biomedical side, the biomedical application side, for example, the pulse amplitude or heart rate or the capture threshold are just all somehow similarly used mechanisms to the grid-based scenarios. I mean, for example, heart rate for the pacemaker, that's the rate can be somehow something like a frequency at the grid-based, energy grid-based system. So we can just end up to some domain-independent results widely, whether they are energy grid-based scenarios or the biomedical side. Still, they are CPS, they have common components somehow in terms of the abstract ecosystem side. So we can just all combine them under a common evaluation aspects, which is really leading to analysis of the attacks and defensive side, and to going further with the XAI and also the digital twin based aspects. So by using the combination, as I already said, that the 7 attacks and 7 defenses, it's end up to 49 combinations with 30 independent repetitions per combination to get a good statistical validation at the end to see the results are all standing well enough in a statistical domain, I mean. So with around almost 30,000 simulation runs, here just all Koaliski correlated synthesis, not PMU already. There's the biomedical side. I need to change this here. And with also some threshold updating, Welford algorithm, I just ended up to the analysis of the flow in terms of a time series graphics, so to see how the user side can observe the change and how the systems just in the cyber duel just acted according to the oncoming AI attack and the defensive technique applied against it. So I will show the demo. Actually, I will show the platform at the end, but there are some findings. Let me to show you some findings when we run that all the simulations accordingly. The defensive technique MTD, it's not a machine learning based technique, as you know. It's just all got the defended the systems in all the scenarios. I mean, totally, but deal with the mostly with the gun grid, the attacking sides, and the attack success rate was 0. But of course, there's the one problem here. The MTD can be causing some early alerts and keep your systems, your grid system or the biomedical system busy. Like, how can I say, like classifying or not distinguishing between the real attacks and the normal flow of the data after a while, because it's a noisy defensive technique here. It's successful, but can result too much success to eliminate some normal communication or some normal data-oriented flows. So Although it was successful, there's the other side of the medallion. And feature security was also successful here, and Bayesian LSTM followed this one, randomization followed this one. The most successful machine learning based defensive technique was Bayesian LSTM technique here. And it's interesting that when we come to the attacking side, as you can see, FTI is stealthy. As you know, this all the physics oriented the attacking system, which just all can be manipulating the target machine learning models like um, the perturbation it does just can simulate some or hide some manipulative chains in terms of data. Or for example, as I already indicate here, it's just all strictly preserve the AC power flow constraints, for example. So it can be all just passing the defensive techniques successfully. Of course, the other the defensive techniques were all successful here, but the FTI has the attack success rate, an average success rate of 8 at the end, with the highest the ranking for, especially when we get it's compared with the adversarial training defensive technique. But of course, for the other things like the Bayesian LSTM or the traditional randomization or GRU adversarial training or Ansible XAI, Ansible machine learning and XAI methods, it's already produced some success. Not zero, but achieved some success. When it is zero for the other attacking techniques, the FTI stealthy was successful enough. So also for all other attacks, it was very, very low, of course, almost zero, but totally that the experimental flow, all the simulations ended up to that the FTI seems to be the most successful attacking techniques, although it's not too high, of course, in terms of success rate, but still it can manipulate your machine learning model or your smart infrastructure, whether it's some energy grid-based system or biomedical device. So also you can see that the other that the methodologies are already successfully fully detected here. The FTI here has somehow a paradox here. The perturbation magnitude doesn't determine the effectives. The physical consistency does. So when we think about that, the grid system or the biomedical system is already connected with some physical aspects, of course, when we go out of the data flow or the algorithmic side, I mean the digital side, and when it comes to the exact the mechanisms of that real system, it's just all about the physical consistency, which is making the FTI still successful. So it has the lowest L2 norm, which means that with the lowest the efforts, the change on the data, it has the highest that attack success rate. So this is the one thing we, as the attacker, the one thing we can we want at the end, because it's the with the lowest chains you achieve high enough or high attack success rates at the end. And for example, for the auto attack and the GSM8, the algorithms, they have the high alter norms, which means that they have too much distance when you compare with the FTI still with the original data and the changed data, and they are fully detected, of course. Even they would have some success rates. The high altitude norms explain us that they can be detected with the newly appearing defensive techniques, because the most the important thing is that making the adversarial data, the samples similar as much as possible to the original data. So of course the Bayesian uncertainty when we think about the Bayesian LSTM, you remember it's the first top machine learning based defensive technique. It's perfectly mimic the normal data perturbations when the attacking is happening, but the defender here measure the confidence, not the distance. So the confidence, the uncertainty and the probabilistic overview, the analysis done by the Bayesian LSTM just all resulted to some of the best defensive flows or the scenarios in the platform. So even when we consider that the generative adversarial network-based gun grid attack creates fake data, which is perfectly aligned with the distribution of the original data, even Bayesian LSTM just detects the attacks and it results to zero success rate at the end. So what the takeaway we can get from this scenario? Even if the data looks statistically normal, the model's internal prediction confidence drops significantly, and this hidden asymmetry triggers the alarm. The asymmetry is the key point here that keeping the defensive techniques successful at the end. So anti paradox. I'm passing this, the alarm fatigue. I already indicated this. This achieves a good detection, but inflates the baseline anomaly scores, risking the fatigue, alarm fatigue here, and making your system not to distinguish between the real attack and the normal data flow. And the role of XAI just all resulting to some feature attributions are already seen here. Accordingly, I will show you the demo. So in order to use my time more efficiently, I am passing this. I use the Shapley XAI here. So when the cyber duel is happening between the attacking scenario techniques and the defensive techniques in the specific scenarios, you are able to see a live XAI interface with the feature attributions are all changed according to the all attack and defense rounds. You can determine the rounds here. You can check and test the application. And even if you see some errors or some problems in it, you can inform me. I can update it. It's just an experimental platform and I want to enhance it in time. Let's see. So the XAI just all results to which features are attributing the more in a positive or negative manner for the detection of the attacks at the end. We have a specific tab for this. And at the end, when we consider this XAI outcomes, it's for the whole total simulations. I will not be going through them, of course, it's taking time. But when we consider the energy grids aspects, the Ph.D is the highest, the one of the top attribution here, or Shapley feature for the 30 of the out of the 39 attack combinations. And is followed by the frequency and the voltage, of course. So this the one physics rational here that the attackers can carefully balance the voltage and frequency to bypass the thresholds here to not to keep you to alert your system. But the resulting physical perturbations here just cause total harmonic distortion. So it's all detected and making the THD as the top feature in terms of XAI side. And similarly for the IOMT insulin pump scenario and the pacemaker ICD scenario, the sensing noise for the pacemaker and the alarm status for the insulin pump were the top features, and also proving that when you go out of the domain, when you are domain independent, it's still the one that the physics rational just all determines the detection success or the detection aspects and triggers the background mechanisms which are just analyzing the physical perturbations and making just alerting the system or causing some alerts when the non-physical normal distributions just all going out of their normal scale, so or normal just values. So it's also a similar thing like the total harmonic distortion is happening to THD to be making the top feature. And here, the one takeaway here that the distributed energy research systems must prioritize the THD sensors as the primary anomaly signal for even for the other regulatory bodies or the compliance, as you know. So the THD sensors are just all here becoming the one critical component. So I don't know if we have any experts in this area. Widely, it's good to hear about this finding at the end. I know that it's important and it's critical, but what if there any other alternative things to consider when it comes to the real applications and the related features we are considering in such attacks and defensive aspects. So when it comes to digital twin, we have the XAI and the digital twin just all shows you the real-time status here. So it also shows some physical nodes, I mean components, which are having some anomaly or just normal running, or have somehow some problems, some alert situation, some breach status, I mean. So it means the anomalous state. So the digital twin allows you such real-time just tracking and detecting the exactly which component, which nodes in your ecosystem, in your or scenario or application just affected by some attacks. So this is the critical thing. So when we combine both XAI, like Shapley or whatever you are using for the explainable AI aspects, when you integrate both of these technologies here, you are able to see, for example, when you see the digital twin is showing some anomalies or the breach status in your system, you can check the XAI side. What are the features causing the digital twin alerts at the defensive side? So if you see that some different not realistic features are detected and caused somehow this alert, so you can see that your system has some problem of trustworthiness. So you may not rely on the digital twin outcomes. So these are just all both these techniques or technologies are working together to approve or to confirm the situation accordingly. One, the XAI is just doing this from the data features side, doing this by using some game theory based methodology, for example, like SHAP. And the digital twin is doing that as that's the real time and all totally connected to your real system scenario, like showing the alert is coming from this component, this node. But what about the XAI side? What about the AI based analysis? Is it correct? Is it correctly detected, or just a false alarm caused by some data-oriented problems on the background? So you need to um, update your defensive techniques. You need to update something there. You need to check there, check something there because your digital twin is affected negatively by some incorrect detections or maybe some bias is over there. So it's the problem. So these are also allowing you to active physical the isolation from passive monitoring, but still you need to combine them accordingly, appropriately for the better results at the end. So the layered defense matrix is one of the outcomes from this application. Like FTI stealthy, the MTD is successful and the supportive shield is the Bayesian LSTM. You can combine them to make the MTD working in an optimal manner, not causing to it's, how can I say, false alarms at the end. If you balance it with the Bayesian LSTM, it's a better calibration. And when we consider the generative adversarial network-based attacks, the Bayesian LSTM can be combined with the Ansible machine learning and XAI methodologies. So the JEM uncertainty here for the Bayesian here just all is successful here, and the XAI supports this, or the traditional machine learning algorithms can detect the simple anomalies in the flow of your data. And when we consider the PGD or auto attack, multiple of the attacks out of the FTI, stealthy or gun grids, you can still use the bias channel STM, and the adversarial training can be supporting layer, another layer. So it results to some strong iterative, defensive the venue for your system. Okay, so you are feel free to scan the QR code here. You can visit my GitHub link here. I generated as a web page like the Cyber Duel in smart infrastructures. You can play around it. I need to update something because after I added the biomedical scenarios, I saw that the some how can I say, console-based commands are still saying something related to energy grid scenarios, but just for example, the voltage needs to be changed with the exact appropriate similar component with the biomedical scenario, so you can accept this when you check the system here accordingly. So let me to show you the demo, and after this you can play around it, of course. Feel free to use it and let me know about your thoughts at that. So I need to also adjust the font size or something here in for better readability. I think, but I will do this maybe when I'm free to update these codes on the background. It's just pure HTML. It includes the many of the things on the as the techniques on the background. Of course, it's not the total advanced high level deep learning or attacking or defensive venue, just a simple HTML based system and using the simple flow of all the attacks and the defensive methodologies. It's not all fed by some data or some other imported something. So this is an enhancement way, I think, that for the future work. So there are 8 different scenarios here. You can select them. For example, the S-Power Utah issue, that's the first US DAR, Distributed Energy Resource cyber attack here. So the unpatched Cisco ASA firewalls at S-Power exploited via denial of service attacks here. So the SCADA and terms lost visibility with for the around 10 hours for the this after for this issue here. Is the reported as the first cyber incident for the distributed energy resources, and there is the EV fleet hijack scenario, the solar farm SCADA scenario, microgrid frequency attack here. They caused the other aspects of the system to be changed, and also when you select them, the default attack methods and the defensive strategies are already here. You can change the attack methods. I already explained in my speech. You can change the defensive techniques also, you see. And you can change the voltage tolerance or frequency tolerance or attack iterations if your attacking algorithm supports the iterative or includes the iterative perturbation generation. For example, FGSM is just all one shot, just all manipulation or change on your data, so it doesn't include. So it's changed according to this. You can check the interface. There's the German wind, that's the NRCon. That's the problem here. It's associated with the Russia and Ukraine war. And also there's a hypothetical reinforcement learning based, pure learning based attacks here, but it's all counterfactual. So because of this, I didn't explain anything about the pure learning and reinforcement learning. It's just somehow something like this. Let me to explain briefly. This system just attacks, the other system defensive technique is defense, and according to the success or failure rate, our attacking reinforcement learning agent just all changes its way in terms of perturbations to try to just defeat the target system or the defensive technique defending this system. Okay, so you can check it also. And IOMT insulin pump pump telemetry application is over here. It's a wireless vulnerability here, allowing the unauthorized alteration of dosing settings, so potentially causing insulin overdose or cessation. So it's just some vulnerabilities reported here. So because of this, these guys just already get the, I think I remember these devices recalled, so eliminated them from the market, I remember, so something like this. And also there's the pacemaker application here. It's not a confirmed real-world adversarial attack, actually, but it's also a hypothetical counterfactual scenario here. But a foundational study just all demonstrated that software-defined radio can reverse engineer and attack ICD wireless protocols. So enabling battery depletion or command injection and unauthorized therapy modification on that's the DR here. So in order to use this, there is even a reported UC vulnerability here. I just tried to define this scenario here. So let's choose one of them. There is the XAI digital twin and some metrics, and those references are already here. You can check them out. So we select this US power, that's the cyber attack here. The Jacobian saliency is the first attacking technique here. The Ansible XAI techniques will already run here. When you start the battle, the cyber duel, you see the red ones are the attacking, and these are analyzed. The orange ones are the analysis by the defensive technique. And if the defensive technique is successful, it sends just some green balls here to show that the successful detection. So it's also reported here in each 10 rounds. I mean, 10 different attacks are all reported here. For example, for the round one, the Ansible XAI detected. For all rounds, I think, for not only second round or fourth and sixth, I think out of these rounds, out of I think the 5 of the all total 10 rounds, it's just all defended or detected by the Ansible XAI here. So sorry, it's all detected. I think there's it's not reported all of them here, but it's all detected with a 100%. So here when you consider the average difference between the changed data and the original data, it's all written here with the L2 ROM. When it comes to XAI side, you can see the shop style feature attribution shows that the voltage here was the top with a very high level of the Shapley value. It's the one of the top first the feature for the attack detection decision here. So the perturbation anatomy shows that the Ph.D and the Rokov the parameters are all widely used for the shaping the attack. These two of the features are used for the attacking. So the anomaly score is just all about the threshold value here, but at the end, the detection defensive technique just all defended these attacks successfully. This is not a real time, actually. I will show it in real time that the voltage deviation or frequency deviation, I mean the foremost, the parameters for the grid systems are already here. You see there are the limits here, and somehow some values are causing to be passing the limits. So in this way, the defensive techniques are detecting the attacks, so resulting to successful attacks. But as you can see, this is the last round. I think there are some anomaly detection happening, like the firewall at the firewall or one link here, but the rest of the other nodes are working accordingly in a normal mode. But this is the last findings, just result to at the end of the scenario. Sorry. So according to this, we can just calculate the detection rates. So, or we can provide some radar graphic to show which are the stealth, stability, speed, or adaptability rates. It's just somehow simulation-based outcomes, but just for showing some additional graphics here. So let me for example, for the pacemaker or insulin pump.
Dr. Utku, we have 1 minute because we're running out of
Okay.
time.
Okay, sure. So let's make it around 16 runs. So let's start the battle. I will just show you the live interface here. You see in each of the runs, the different features are considered in terms of the detection. And these are evolved in rounds. So you see which of the parameters, features, attributions are widely used for the attacking side, like flow rate. Flow rate corresponds to THT for the grid scenarios, and sorry, alarm status corresponds to THT. And this, I think, the voltage or something like this. You can make them as something like similar, not total same thing, of course, but something like this. You can make connections here. So this is the digital twin side. You see if there's any problem in terms of some nodes, it will be showing anomaly. Like, for example, the hospital VLAN includes some anomaly. The rest of are working normal. I think why I'm taking a look at to this, it's already stopped and handed here. You can see the runs here. I think I need to update some codes to show the other runs here. It's showing some maybe the most successful runs here, but I need to check the codes on the background. So this is a playground. So this is a simulation here, and the results, the findings I already explained to you during my speech are with all the combinations I'll run with the different parameters here. So that's all. I hope you can just understand how the XAI aspects or digital twin can lead to a better defensive strategy and how the cyber duel can be happening here with the different attacks and defensive techniques can be all tested in a common environment and enabling you to test some scenarios and to go further for the designing these things in a real manner. So thank you very much. Your all questions are welcome. I will stop my presentation.
Thank you so much, Dr. Utku, for the great presentation. So we'll open up the Q&A. Folks can place their question. Okay, maybe I'll start with one question while we are, okay, so this SHAP feature that you use, you are saying that based on the attribute of SHAP feature, which is going to be dynamically changing, but attackers are using row cough and THT, right? Is it because this rate of change of frequency in THTs was picked because the scores were low, or can you provide some insight on why attackers are choosing that? Or am I not listening to that?
Yeah, you mean that the Shapley values, the resulting Shapley
Because
rates,
you said 140 out of 49 instances THD was a top sharp feature, right? And then I saw some other slides. Maybe I was confusing between two different projects. So the question is how should one take away from this talk? Are you saying sharp feature is one way that you could able to
yeah. Yeah, actually not only one way to detect the exact feature here, but I mean, my application is just use the Shapley methodology to showcase which features can be or evaluated for designing a trustworthy tracking mechanism. So the THT actually just the THT, that's the value, the value is just all related to the some mechanisms of the grid systems to get the understand the distortion. If the distortion happens, then it can alert the whole mechanism. So it's a normal thing. So it's there are lots of other stuff on the background, but the THT or such physics-oriented, that the physical-based connections are the exact features which can be used as some defending mechanisms to check and to analyze, to alert the systems. I mean, you manipulate the data, you play on the digital side with your attacking techniques, but still the THD is something in the physical world, in the physical side, in the CPS, can be still effectively used for dealing with the attacks. So the Shapley methodology just showcased this as because the THD is the top one. The real system, real things are just all tends to be better analysis or the defensive actions can be taken.
Super.
Yeah.
How about others? Any other questions people want to jump in? The 20
Yes.
folks here. We need a couple of
Yeah.
questions, good questions. Is there a reason why you chose
Yes.
L1 norm that has 0.177? You talked about, you're using L1 norm as a metric for what purpose?
Yeah, it's just for the understanding how the AI attack technique just changed the distance or change the or make the original data or the manipulative data different, adversarial data different from the original one. The lowest value means that if you are successful with lower values, with the lower norm values, that means you are more stealth or you have a stealthy AI attack technique. If it is bigger, then defensive techniques can be detecting your adversarial data samples. So the target, actually, in the literature, the one of the most important target or the research aim in the developing AI attack techniques is the keeping these norm values, the differences between the original data and the adversarial data samples small enough with
Great.
small perturbations and keeping it small still. Yeah.
I do enjoy that moving target defense discussion on, how it breaks the physical constraints, and
Yeah.
in your use case, you're talking about how it can help in alarm calibration. And, can you talk a little bit more about what, so many students are listening, and what is the future direction that people should focus on when we talk about MTD, and also some light on auto attack.
Yeah. Auto attack actually just all designing the things. I mean, like hybrid attacking techniques. You can still design or you can recall the FTI still or other stuff in a common way to go further and to make the things more difficult for the defensive side. But still, when we still use some effective even Bayesian based defensive techniques, as you can see from the findings, they are still failed at this point. And the MTD needs to be regulated with the other system, you know, that with the Bayesian LSTM, because only traditional techniques, which are not including AI flavor, I mean, are not useful anymore for advanced attacking techniques. They may be effective for maybe traditional, simple attacking techniques, cyber attacks. But when it comes to the AI-based attacking techniques, the MTD can be successful, but too much, too high level traditional thing, which is like, how can I say, a very basic and simple binary decision based technique, in my opinion, because it starts after a while, it starts to make the everything, to act to everything seriously and make the or make alerts for even the normal data flow. So in order to deal with this, the combination of the AI-based techniques and the traditional techniques will be key point, I think, for even against the very successful attacks like auto attack or FTI stealth here. So
I think you touched it in your demo. I think you talked about, even though this is a more digital twin type of thing to show, what those scenarios may look like. How do you
yeah,
see when we bring edge computing, in terms of these needs to run on some hardware. These needs to, have some security protocols in place when these DERs communicate with each other. Their communication overhead is so low. How do you see this is all going to go forward? as we look at futuristic implementation perspective, right? And from a digital twin, it makes sense. What is
Yeah.
your vision? How do you see maybe, how do we handle this in terms of implementation?
Yeah, actually, I didn't include this mechanism here. Maybe it can be a future work. The digital twin actually somehow in my application is somehow some instant tracking mechanism and with some descriptive outcomes, like showing you some more hidden things or just making the user site easily seeing the things. And one other mechanism for the digital twin is just all including the advanced AI aspects for the predictive outcomes. So when it comes to some early alert detection or some maybe detection the future state of your the components of your nodes, even when it comes to edge computing, like edge-based low resource running systems. The basic digital twin contributions and maybe establishing a central tracking management system can expose some predictive perspective over your whole system, a big system. So
Thank
for
you.
the future, you can act immediately. You can be one step away from the potential attacks or the manipulative scenarios. Yeah.
Super. In the interest of time, I'm going to stop here with the questions, but I appreciate for being here and this morning, and
Yeah. You're welcome.
look forward to continue to the collaboration. You need to help us promote the cars, and
Yeah, sure,
we'll,
sure.
we'll
Always.
talk. Thank you so
Yeah,
much,
for
Dr.
sure.
Gupta.
Thank you so much. Thanks so much, everybody. See you.